Connell is a well-known and major contributor to the global stability of epidemic models involving time delay and structured variables. Today he's going to speak to us on accounting for heterogeneity in social distancing. Connell, please.
Okay, thank you for the opportunity to present. My commute this morning was a little less than it usually is for presentations, so yeah, interesting times we live in. So what I want to talk about today is the idea that some people are better at social distancing than others are. And if you saw any news reports from this past weekend, at least in Ontario where the weather was very nice, you would have seen photos to reinforce this idea. I'll show some pictures about that in a little while. And when we do a lot of disease modeling, if the situation is good, you get some data, and from that data, you calculate the parameters that you need for the system you're studying, use those parameters, make projections, and carry on. In going through that process, when you calculate your parameters, very often you work with the average value of some parameter. You realize that some people are taller than others, but maybe you work with an average height if you're dealing with something where height matters. Some people are going to recover from disease more quickly than others, but often work with the average value for the recovery time. There are going to be some situations where that's perfectly acceptable to do, but there are going to be other situations where you're going to lose some detail about what's important by working with the average values. And so I want to work with the idea of heterogeneity in contact levels or in social distancing. They're kind of equivalent. Social distancing is to reduce your contact levels. So I want to look at the idea of having different groups that are social distancing to different degrees and see what impact that has on the disease dynamics. So here's the basic model. So there are 7 groups here, and a lot of these are familiar. If I just shoot ahead for a moment, we have a susceptible class, and everyone below or nearly everyone below the top level is sick. Down a little lower, we have a recovered class, so they're recovered. Hospitalized group, and in our model, the hospitalized group will just be essentially taken out of the population until they've recovered. We're going to assume that once they're hospitalized, they are not interacting with anyone. Not a perfect assumption, but we're going to work with that as a simplification. And then these 3 that are in red here, these are the infectious groups. These are the ones that can actively spread the disease to other people. And we have the exposed class at the top. So back to the picture. Oops. So individuals start as susceptible over on the left. There's this infection rate gamma that'll move them into the exposed class. They'll be in this exposed class. And these are latently infected. They are not infectious. So this is where you've caught the disease and you have 2 or 3 days where you're not suffering any symptoms of the disease and you're unable to spread it to anyone else. And then individuals move into this asymptomatic phase, class A, where they still don't feel any symptoms of the disease, but they're now infectious. So they can wander around not realizing they're sick at all and spread the disease to other people. And this does seem to be one of the big drivers for COVID-19. From there, I have IS and IM, and these are kind of your classic infectious cases. They're people that feel sick to varying degrees and are able to spread the disease to others. The IS is the more serious cases, and down below we have the IM, which is the more mild cases. The serious cases, IS, can potentially move over to being hospitalized, and from hospitalized, they can either recover or die. There's a default death rate, this mu-S, mu-E, mu-A everywhere. These are just the background deaths that get hit by a car, die of old age, whatever, that affects everyone. And then the only additional death rate in this model, built into it, comes from this hospitalized group. So it's assuming that anyone who gets serious enough to actually die from the disease finds the way into the hospital first. All of the red groups here have arrows over to the recovered class, at which point they're safe, and in this model, the immunity is assumed to be permanent. So that's the basic model. There's nothing about social distancing in here. Some things that are not included that are clearly important, but for the purposes of looking at heterogeneity, we can leave them out, I think, too much worry. So there's no quarantine, no long-term care homes, and no substructure within hospitals. And these are things that do show up in some other models. Differential equations. So we had 7 nodes in the previous transfer diagram. So we have 7 equations here. Each of the variables, so with the heterogeneity and social distancing, I'm going to have 2 groups. There'll be the social distancing group and the non-social distancing group. So my susceptible class can be broken into 2 groups, S1 and S2. The asymptomatic class A can be broken into 2 groups, A1 and A2, and that goes the whole way through. So all the variables here should really have a subscript J, where J is either 1 or 2. It just becomes a visual mess if all that detail is put in. The impact that the heterogeneity has shows up in 2 ways in the equations. This incidence term, the gamma J, this gives the motion from class S to class E, or I guess from class SJ to EJ. That's going to depend on which group you're in. Obviously, the groups that are having more interactions are probably going to move more quickly from SJ to EJ. And then the other impact, or the other way that the heterogeneity shows up, is I have to split the population into the social distancing group and the non-social distancing group. And we do that, we just say a certain fraction F is going to be in group 1, and the rest of the population, 1 minus F, is going to be in group 2. So the FJ here is just a fraction of our population that's in the 2 groups. Think of it as the relative sizes of the 2 groups. Everything else that shows up below is standard, fairly standard stuff for compartmental models. Yeah. So there's a group of people that are social distancing properly. We've probably all gone through this at some level, getting groceries or something. Lovely weather in Southern Ontario this past weekend, and this is what one of the parks in Toronto was looking like. So I think particularly as the weather gets good, you're going to find that a lot of people are either giving up or getting lax or taking breaks from social distancing. And so this clearly, I think, is going to be a big driver in how things can unfold in the future. So I'm going to assume there are 2 groups. Group 1 will be the social distancers. So the contacts for the population will be given by C, so the average number of contacts. For the social distancers, I'm going to have this multiplier tau1 that reduces their contacts from C to tau1. So if it's 0.5, then they're only having 50% of the contacts that they were having a few months ago. N1 gives me my total population of people that are having contacts that are in this social distancing group. There is an H1 group. These would be the social distancers that end up in hospital, but we're assuming that they don't have any contacts. Then group 2 is the non-distancers, and these might be the people that we saw in the Toronto park there that are choosing to not distance. It might be reasonable to also throw in healthcare workers that, due to their jobs, are unable to avoid lots of contacts, so they could be in this group as well. But without worrying too much about who's in this group, we'll just take it as we have 1 group of distancers and 1 group that is not distancing. The total number of contacts per day, you just take our population sizes times the number of contacts that they have, so C tau1 N1 plus C tau2 N2. If I want to look at the probability that a contact is with someone in group A1, I take my total contacts in the denominator here, and the number of contacts that someone in group A1 is having, and I get this fraction. I want to switch it to someone in group IS2, so this is the serious infections in group 2, the non-distancers, then I get a very similar fraction. So for a basic SAR model, I'm going to use proportional incidence, which I think a lot of the COVID models are using. The incidence is, so C is the number of contacts, beta is the probability that a contact between a susceptible and an infectious individual actually results in transmission. Someone who's sick sneezes on you, maybe you get sick and maybe you don't, or they're speaking with you, maybe you get sick, maybe you don't. So that probability here is the beta. So C times S is the number of contacts that the susceptible individuals are having. A fraction I over N of those contacts are with infectious individuals, and then the probability of transmission happens is beta. Okay, so that's what I just said. So in our more complicated model, because we have more infectious groups, A, IS, and IM, and then each of those will have a subscript 1 or a subscript 2, we have to figure out what's the proper term. So for incidence from group 1, the up above, where we had C beta S, let's look at the CS from up above. We now have C times S1. we have C tau1 times S1. This gives the number of contacts that individuals in group S1 are having per day. And then what's the probability that they have contacts with people in all the different groups? And some of those probabilities is in this giant fraction here, as well as the beta. So I'm allowing initially that people in the groups A, IS, and IM might have different levels of infectivity. So this gamma 1 is the incidence rate for susceptibles in group 1, similar fraction for group 2. And the only difference between the incidence in group 1 and group 2 is the stuff that shows up in orange here. So the contact rate becomes C tau 2 instead of C tau 1. And the number of people having these contacts is S2 instead of S1. But the giant fraction on the right-hand side is the same for the two groups. Often that might be called the force of infection. So differential equations, again, if I put the subscripts on all the variables here, this is a 14-dimensional system, which means pencil and paper calculations are a little tricky, except for some of the very specialized ones. So mostly what I've done is numerical simulations. Anyone who's familiar with my work at all probably knows that I really don't do a lot of numerical work. So I've been developing new skill set over the last couple of months. And through the numerical simulations, kind of see some stuff that I would never have been able to figure out, even for a much simpler model with pencil and paper calculations. So given that I have a social distancing group with this multiplier tau 1 and a non-distancing group with a multiplier tau 2, where tau 2 is equal to 1, so no reduction in contacts for group 2. If I have two numbers, positive numbers, Q1, Q2, that add up to 1, then I get a weighted average of the taus. So I'm going to pick my Q's to be these kind of messy fractions, and if you add them together, you get 1. So I can use these to get a weighted average of the contact multipliers. This will be tau star. And then filling in for the Q's, I get a bigger expression, and remembering that F1 and F2, these are the probabilities that individuals are assigned to either the social distancing group or the non-distancing group. I can turn them into Fs. So if I know what tau 1, tau 2, and F are, I can calculate tau star. So if you go back and use the next generation matrix method of Watmow and Van der Biesche, then the expression you get for the basic reproduction number, it doesn't tau 1, tau 2, and F don't appear explicitly in here. You can just replace, kind of the way they show up is in this larger parameter tau star. And these T's here are just average times. The TA appears in the other T's, so those are actually quite large expressions. And normal thing with R0 is if it's greater than 1, the disease can invade when you're near the disease-free equilibrium, and if it's less than 1, then the disease cannot invade. When you get further away from the disease, for many levels, if R0 is greater than 1, then the disease will survive, and if R0 is less than 1, then the disease will die out. That global behavior doesn't always work when you move away from the disease-free equilibrium, but it often does anyway. So it's usually taken as a good indicator of what you have to do to get rid of the disease. So this tau star, I think of it as the effective contact multiplier. And effective contact multiplier, because in R0, tau star is the multiplier that shows up there. C tau star is like the effective number of contacts that people are having. If you know those, so is it sufficient to just use that tau star? For finding R0, yes. If you want to find the doubling time for the initial outbreak, then it's sufficient for that as well. So what you would do there is you would calculate your Jacobian matrix, evaluate it at the disease-free equilibrium, look for your dominant eigenvalue. That'll give you your instability. If R0 is greater than 1, that dominant eigenvalue would be positive. And clearly, we had that a couple of months ago. From that eigenvalue, you'll get the exponential growth that happens. From that exponential growth, you can calculate the doubling time. And it turns out, when I did this numerically, I found that as I messed around with all my parameters, by keeping tau star fixed. So when I messed around with tau 1, tau 2, and F, keeping tau star fixed, the doubling time stayed constant, just as R0 did. So for the doubling time, it seems that the tau star is sufficient for that as well. But when you try to find where the peak of the outbreak is, or how high the peak of the outbreak is, tau star is not sufficient for that at all. So I want to do a numerical experiment. So I want to keep tau2 and tau star fixed. So again, tau2 is that multiplier for the non-distancing group. So tau2 is just equal to 1. I want to keep tau star fixed, and for a lot of what I'll show you, I use tau star equals 0.7. So we're assuming that whatever tau1 is, we're able to do somehow choose f appropriately in order to keep tau star fixed at 0.7. That keeps R0 fixed at one value. It'll keep the doubling time of the outbreak fixed at another value, which means the initial outbreak in all the simulations I show will look exactly the same. I do play around a bit with changing tau2 and tau star. I probably won't show any of that today, but what I show you isn't just a fluke from very special parameters. I've played with messing around with parameters or varying the parameters. Things still persist. So here's tau star as a function of its input parameters. I can rearrange that and get f as a function of tau1. Because I'm thinking of tau2 and tau star fixed, I think of f as just a function of tau1. So if I choose a value of tau1 and then choose f according to this formula, that will guarantee that tau star stays fixed at its value. So it'll stay fixed at 0.7. So for each value of tau1, as I vary that, I'm going to plot solutions to the 14-dimensional system and see what happens. So probably about 20 parameters in the system. So just a short word on that. The contact rates, the basic contact rate that I used is around 13.5. It comes from work that was done 12 years ago in the well, they looked at a bunch of European countries. I took the data from the UK in particular. Actually, what I did is I followed work by Tuitt, Fisman, and Greer that came out recently. They took data from this paper. I went and tracked down the paper and figured out an average contact rate. And right there, I'm kind of falling into the trap that I'm saying you shouldn't fall into. I found an average contact rate, and I didn't look at heterogeneity at that point. But I introduced it later and hopefully show that it is important to look at. The R0 I'm going to take to be 2.3. And this comes from work done a couple of months ago studying the outbreak in Wuhan. And in different places, the value of R0 can change. So there's kind of a range of values for R0 that are appropriate, but 2.3 is in that range. And this is R0 in the absence of any social distancing. Most of the other parameters like recovery rates and latency periods took from Tuitt, Fisman, and Greer, and they cite where everything came from for that. Since I didn't have any access to information saying how the values of the different betas would be different, for my numerical simulations, I used the same value of beta for all of them. I did experiment with taking different values for the betas, and the same phenomenon that I'm going to talk about continues there as well. But this beta is actually a very tricky thing to measure empirically. You want to find out what's the probability that an interaction between a susceptible and an infectious individual results in an infection happening. But it's not even that easy to specify what counts as a contact between the individuals. So if I just walk next to someone on the sidewalk, we're not supposed to do that anymore, but is that a contact? If I'm too close to someone in the grocery store, if I go for supper with someone, so there's lots of things that could be a contact, given that we're talking about a respiratory disease. So just sharing air and fluids and stuff is how it's spread. So using the value of beta of 2.3, all the other have, you can, the only unknown that I have is beta, so you can reverse engineer it and you figure out beta has to be roughly 1 over 40. You can note that if tau star is less than 1 over R0, then we expect the disease to die out. So R0 is 2.3, so if tau star is less than 0.4, roughly, 0.42 maybe, then the disease should die out. So here's the simulations. If we look at the left-hand panel first, so tau star, this effective contact rate that we're keeping fixed, is equal to 0.7. And if we start by taking tau1 equal to 0.7, then you should just have everyone in group 1, everyone in that social distancing group. No one's in the non-distancing group, and that'll guarantee that tau star is equal to 0.7. And these are the plots here. In the other two panels, you can see there are blue curves, red curves, and green curves. In this panel on the left, unless you look closely, you don't see the red curve. The red curve is directly underneath the blue curve, because the blue curve is the total population. The red curve is group 1. But in this panel, group 1 is the total population. The green curve down here at the bottom, this is the non-distancing group, but since f is equal to 1, the non-distancing group is empty, so the green curves just go straight along the axis. The size of the groups are equal to 0. So what we're finding here in this left panel is if everyone's in the, if we assume that everyone is social distancing at exactly level 0.7, so a 30% reduction in contacts, then we get this peak up here. This peak is the number of current infections, so it's all of our groups added together except for the cell group. And it seems to peak at around, let's see, that'd be 600,000 people. And I will say, I don't think the numbers that I end up with are totally accurate because I haven't done a deep dive into the parameter fitting or anything. So, but we're getting a peak here around day 200, 600,000 people. Current hospitalizations is somewhat lower than that. The cumulative death total rises up to something like 20,000 or maybe 18,000, and the number of susceptibles decreases. When we get to the end here, the far right-hand side of the first panel, then there's no one left, or barely anyone left in the infected groups, hospitalized group. Some people have died. So there's a lot of people who have moved into the recovered. The drop in height in the susceptible curve from the beginning to the end is accounted for in the recovered population, which has gone from 0 to fairly large. Okay. In the middle panel, same idea, but now tau1 is equal to 0.4. With that value of tau1, we want to choose f equals 5/7, and that'll guarantee that tau star is still equal to 0.7, just like it was in the left-hand panel. What we find here is that in the top portion, the peaks have all gone down. Well, the blue peak and the red peak have gone down. The green peak has gone up from 0. And that's just saying that because we now have people in our non-distancing group, there's now an outbreak in the non-distancing group as well. And mostly, I think the top portion of these three pictures are the ones to focus on. So as tau1 decreased from 0.7 to 0.4, we found that there was a drop in the height from the top of the left panel to the top of the middle panel. And when we go over to the top of the right-hand panel, it has dropped down again. So here in the right-hand panel, tau1 is equal to 0.1. In that case, we want f equals 5/6. So 5/6 of our population will be in this social distancing group. And that'll guarantee that tau star is equal to 0.7. We find that the peak has dropped dramatically from the left-hand panel to the right-hand panel. There's been about a 70% drop in the height of the peak from assuming that everyone is equally social distancing at 0.7 versus social distancing being broken into one group distancing at level 0.1 and then the non-distancing group at a level equal to 100% of the contacts. Then note that the axes here are kept fixed between all three panels. So the visual difference that you see is genuine. Okay, so see if I can switch to a video here. Okay, so this video shows 100 simulation of 100 different values of tau1, decreasing from tau1 equals 0.7, which is equal to tau star, all the way down to tau1 equals 0.1. And two interesting things. One, very obviously, as tau1 decreases, so as we go forward in time, tau1 is decreasing. As it decreases, the height of the peak, just looking at the top portion up here, the height of the peak decreases substantially. The other thing is that the peak doesn't move left to right. And that part really caught me off guard. So right here, I'm now showing these two plots are summaries of the video. So on the, let's take the one on the right-hand side here. For all the different values of tau1 goes across the horizontal axis. I'm plotting the height, the time at which the infection reaches its peak. And it's essentially constant. The little variation that appears here, I think, is more numerical in nature rather than anything substantial. I think it comes from maximizing vectors rather than maximizing a continuous function. But the timing of the peak essentially stays constant at a little bit less than 200 days. In the left-hand portion of this, so now the video I showed a minute ago, it begins over on the right-hand side of this left-hand picture when tau1 is equal to 0.7. And as the video progressed, tau1 was left in this picture. And on the vertical axis, what I'm plotting is how high the peak is. And what we see is that the peak, as tau1 decreases, the height of the peak decreases monotone. And again, this has about a 70% decrease in the height of the peak. When I played with different values of tau star, sometimes the percentage loss in the height of the peak wasn't as significant as was here, but it was always above a 45% drop. Yeah, so the degree to which this phenomenon is happening may not be as extreme as what I'm showing here, but I think it really is a persistent phenomenon that carries on with lots of different parameter values. Okay, now another video. This video is showing the fraction of each group that's infected. So as it turns out, in keeping tau star constant, at least at 0.7, the social distancing group is always much larger than the the social distancing group is always much larger than the non-social distancing group. And that's just a matter of the way the parameters are chosen. With the 0.7, I think the largest your non-distancing group ever gets is about 30% of the population. But if you look at the fraction of each group, as tau1 decreases from 0.7 to 0.1, we find that we saw in the previous video that the height of the peak of the outbreak decreases dramatically. But if you look at the fraction of each group that decreases, or sorry, the fraction of each group that is infected and how that changes, there's only a small change in the fraction of the non-distancing group. It probably went from about 12% to 10%, whereas the distancing group, as they distance more and more, this red curve got very, very low, showing that their distancing, at least protected their group. Yeah. So, small observation. As tau1 decreases from 0.7 to 0.1, keeping tau star fixed, and keeping tau2 also fixed at 1.
It's Jiang Hao.
Yes.
Can you help us again to recall what tau star means? I mean,
yes. Yeah. So it's the often when we so we're given data, you calculate some parameter values, and a very natural thing is, if you have 10 people, you could add the values for those 10 together and divide by 10, and you get this average value. And we think of that as representative of the appropriate value for that parameter. And when we're calculating R0, it turns out that, and what you've done there is you've calculated a weighted average of those 10 values, and that weighted average is a uniform average. This tau star, it's an average between tau1, the contact multiplier for the distancing group, and tau 2, the contact multiplier for the non-distancing group. So it's a weighted average of those, but it's not a uniform average. We're not just saying that if our population is split 50-50, that we just take the number halfway in between. What we do is we go back to the formula here for tau star, and it's a different weighted average of tau 1 and tau 2 that takes into account the fact that the people in group 2 are having a lot more contacts than the people are in group 1. So if I want to know who am I most likely to have a contact with when I have a contact, if the two groups are of equal size, my contact is much more likely to be with the people in group 2. And so what tau star does is it gives this effective contact rate of the population as a more appropriate weighted average between tau 1 and tau 2. And this weighted average of tau 1 and tau 2 is the value that should be used for calculating the basic reproduction number. That comes out of the next generation matrix. And it also is used for calculating the initial rate of exponential growth, or the doubling time at the beginning. And that would come out of the Jacobian. Okay?
Thank you. Yeah.
Okay, so when we keep that weighted average fixed, and one of the things you can think of is it allows you to divide your population into a distancing group and a non-distancing group while still taking R0 as a constant. So suppose from data we're able to tell that R0 is 1.6. So having a drop from 2.3 to 1.6, that's a 30% drop. So these are the numbers that I've been using. If we have that 30% drop, then we say, oh, tau star must have dropped from, I guess it was 1 when everyone was out when everyone was out interacting at their normal levels. It's now dropped to 0.7. And that would give us this new value of R0, 70% of what it was before. But if we think about the groups, we know that there are some people that are doing quite a bit of distancing and some people that are doing not so much distancing for whatever reason. And by keeping tau star fixed and varying tau 1, it lets us play with the idea of that distancing group being, are they distancing a little bit more than the others? Or are they distancing a lot more than the others? And seeing what the impact is. And from the plots, I think it shows that the distancing could be quite important. So the height of the peak can decrease quite dramatically. So for a while I was quite caught up in that, and to start thinking about it, the tau star is not really an input parameter. If you went out and started measuring your population and what they're doing, you wouldn't start with tau star. If you were able to do really good survey data, and this would be no easy thing to do, but you can imagine, conceptually at least, being able to figure out the contact levels of your population and how much social distancing they're doing. And you would almost certainly find that there is going to be a lot of heterogeneity in there. So what would you do? You would approximate the data with a bunch of different contact levels, these C1 to Cn. If you like, those can be written as a single C multiplied by a bunch of taus. And you'd have the fraction that's in each of these groups. So like a histogram would do this. You find your fraction of your population that's in each of the bins. You can calculate an average contact level, just a standard average, how big are each of your bins, and you assign the appropriate weight for them. That's not what we want. We want something that makes use of this tau star. So if we let tau I be equal to Ci over C bar, and you can use a different denominator there. It doesn't matter. It all comes out in the wash afterwards. We can calculate this tau star. So this is the same formula that I had before, except I only had it for a sum over two different population groups, but should continue more generally than that. So the R0 could come from other data. So maybe we find that R0 is equal to 2.3. We have our C and our tau star. I should probably have a C bar here instead of a C. That's a little typo. And the betas would be the unknowns here. So you could reverse engineer those like before, and we'd have our data. Now, one of the comparisons that's worth making is, what if we ignore the tau star? What if we just use the average contact rate? So for R0, instead of having C times tau star, what would happen if we just use a contact rate C bar that we have up here? What would that give in comparison to the types of plots that I was showing a little while ago? And the blue curve here is what I showed you before. So the blue is the using two groups letting tau1 vary from 0.7 all the way down to 0.1, plotting the height of the peak goes from almost 600,000 down to 170,000. So about a 70% decline. And if you use C bar instead, so instead of that, what I'm claiming is the proper weighted average of contacts. If we just use a standard average, what we find is the predicted height of the peak starts at the same place when everyone's in that same group, but as tau1 decreases, we end up with this red curve going down, and it decreases much more dramatically. It even goes all the way down to 0. One of the things that happens is what I was doing, where I'm keeping tau star fixed, that keeps R0 fixed. But if you use C bar instead, then C bar will decline with tau1. What you find is when instead of having R0 stay fixed, like I believe it should, you have C bar decreasing, and therefore your belief in what R0 is decreases. Eventually you end up with R0 getting below 1, and you think the disease is going to die out, when in fact that's not what happens. We're actually much higher up on the blue curve here. When you look at the timing of the peak, so over on the right-hand side, at the far right extreme, they're both equal. Everyone's in the same group. And as tau1 decreases, even though the height of the peak decreased from our left-hand panel, in the right-hand panel here, we find that the timing of the peak increases. It increases up in this nice curve here. And then I've actually no idea why it flattens out here. I don't understand that. I haven't had a chance to explore it. And then suddenly it jumps all the way down here. And the reason why it jumps down is at this point, the R0 is below 1, and the maximum is right at the beginning. And so what you see here for the timing, that's really just saying that there's no outbreak whatsoever. So using just the straightforward average contact number rather than C times tau star, I think gives quite inaccurate estimates on how high the peak would be and when the peak would occur. So this just reiterates the last slide. So if we use only one group with the average number of contacts C bar instead of C tau star, predicts a peak that's too low and too late. If we use only one group, but we just assume C tau star contacts, that predicts a peak that is too high, but at the correct time. So in the plots I had, going back to here, that would correspond to in my left-hand panel at the top right corner, C star, using a value C tau star for everyone, without breaking down into group 1 and group 2, corresponds to this top right blue point. So we get a peak that's higher than I think it should be. If we use two groups, then the height of the predicted peak could be substantially lower than one group. So that's on the same previous diagram. When we use two groups, we move down and to the left on that. And the second video I showed, the infection group hits the more active group at a percentage level harder than it hits the less active group. And that's kind of what you'd expect. The people that are out having lots of contacts are putting themselves at higher risk of catching the disease. So my claim is that properly accounting for heterogeneity in contact levels and social distancing is important. So some stuff to look at in the future is, I'd really like to figure out the height of the peak as a function of the input parameters tau1, tau2, and f. And Jane Heffernan kind of steered me in that direction with a good reference, so I think I can make some progress on that. I haven't done any calculations for when there were more than two groups of, or two levels of social distancing, but what I expect is a similar phenomenon, but likely less extreme. Having two groups, like a perfectly bimodal set of data, is probably the most extreme that you're going to find. So the in reality is probably a less extreme result than what the simulations here show. And that kind of leads into the idea of how much heterogeneity can there be in these contact levels before it becomes important. If there's only a small bit of heterogeneity, then you probably just ignore it, keep things simple, and get very appropriate predictions. And that's the end.
Thank you, Connell. Kuma is there, so Kuma, you, how do you want to proceed with questions?
So I will let you handle the questions, except that I want to ask the first question.
All right. So anybody who want to ask a question, you can send me a WeChat, or you can wave your hand so that Brian can unmute you.
So,
yeah, Kuma.
So Connell, I understand that you looked only at two groups, but do you have qualitatively an idea what happens when the number of groups grows?
Yeah, so if okay, so if we look at the graph here, and ignore the red. The red is what you get when you do something wrong. So with the blue curve here, this was two groups where, so tau 1 is decreasing from 0.7 to 0.1, tau 1 is held fixed at 1, and we'll keep tau star fixed. I think if you add more groups and I don't know, you start playing around on some parameter manifold that keeps tau star fixed, what you'll find is the blue dots are going to be somewhere between my minimum and maximum here. I think having more groups will have a dampening effect on what I'm showing here.
That's interesting. I agree with that. I think that's exactly what's going to happen.
But for the right-hand panel, where I'm showing the timing of the peak, actually, I found very bizarre that that came out to be a constant. I suspect, wouldn't bet my house on it, but I might bet my car on it. I think it stays constant for multiple groups there as well.
There's some work you would probably be interested in of Troy Day, where he's trying to look at this de-escalation strategies, where you have multiple groups. So they will be, he's working with two groups, but there it's very clear that the things get better if you have more groups. I mean, practically it might be impossible to execute, but it actually numbers get better if there are more groups.
Right. I definitely think that as things open up, you'll find different people will have different levels of buy-in on how safe it is. So there'll be a lot of people that keep the distancing very low, and there will be some people that are just desperate to get out there and do things again. So the reopening, so this idea of heterogeneity, I think really has to be explored for the reopening and see what impact it will have.
Very interesting. Okay, thank you.
So actually, it's Jiang Hong. I have a relevant questions. Maybe you can going back to the real expertise in structured population model. Maybe you can just structure the population by the activity levels, so you can have a continual partition of the population by the activity levels. Will let you really address Kuma's questions.
Right. So I think so right here where I have the summation, essentially, we have the continuum of taus there, and the sums would turn into integrals. And I think that's a very natural way to go with it. When it comes to trying to do simulations, at some point you probably end up breaking it back down into a discretization, but for pencil and paper calculations, which I think you can get a good bit of progress on those, the continuum is a good way to go. It's one of my, I probably should put that in future work. It's definitely something to do.
Before I think I want to add a remark, and on behalf of Kuma and the fields, and once thank you not for bringing your colleague from Wilfrid Laurier. I think it's feels as strong desire to bring all the neighboring universities together, and this is a good opportunity to see many of our colleagues from Wilfrid Laurier. Now I have the next question, Masoud van Deef.
Yeah, oh, thank you. So as we know, disease dynamics may the same spirit as the Kumar and John Hong say. So as we know that the disease dynamics differ by age. So therefore, it will be interesting to consider the three group in the beginning. This is the moderate group. So the young generation, they are usually prefer non-distancing. So the moderate age prefer the more or less, and and then also the age more than 60. So that this is, I am thinking that 20, 35, 60, and more than 60. And in this case, it will be, as in the spirit of the previous questions, it will be, we can start from these and taking, maybe in this case, we can easily compute this function depending on your three parameter. This will be the one of the way to start with the not only two, but three groups. And in this way, I guess we can also say which group could be dominated. So computing the reproduction number and see that, say the one group, the reproduction number more than the others. And so the one group could eliminate others. So it will be one of the also the promising direction, I guess. What do you think?
Yeah, so when we look at who's in the different groups, I think you're right that there's a lot of correlation between people's ages and what group they would be in. And moving it to three groups is kind of a very natural thing to do. It's probably it's still fairly broad strokes to say that it's only three groups that'd be relevant, but it's probably a decent enough approximation. When you calculate the R0, I guess so Van der Driesche and Schwei have their stuff on the breaking down the basic reproduction number into the contributions from the individual groups.
Yes, exactly. Mm-hmm.
And so you probably start to spot that that's probably a really good tie-in to looking at the heterogeneity. And the one way to look at it is finding out who to blame, but maybe a better way to look at that is finding out which group do you have to advertise to or educate or try to get them back on board, and where could you have the greatest impact in trying to.
Yeah, this is exactly what I'm thinking.
Yeah.
Mm-hmm. So how it could be also just the last question. Could we incorporate some other kind of heterogeneity, like the spatial, the geographic? So because it depending on the geography.
Yeah, and I think there's something important there. I didn't say this. The simulation I did, I ran with a population of 6 million people, meant to be the Greater Toronto area, and people in Toronto are not going to affect people in Ottawa and stuff. So there's definitely a breakdown between who can spread to who, or who can spread whom. So you can do a meta population model there, where you're looking at the ability of people to spread from one group to another. So the contact numbers that you have, maybe it becomes a CIJ, where one subscript talks about what group you're in, and then the other is what group you'd be infecting.
Yeah.
And the paper I mentioned, Tuit, Fisman, and Greer, they have I think some of that built into the age cohorts and how they would interact with each other. So there's lots of heterogeneity that shows up in lots of different ways. I think in the contact structure is probably the most important part to have, and whether it's contact between different locations, different age groups, different activity levels. rather than in recovery time. So it's more of a linear problem that probably comes out in the wash there a little bit more. But where the nonlinear terms are, I think that's where there's the greatest chance for heterogeneity in parameter values to kind of confound the predictions we make.
Maybe it's Jianhong again. So maybe we can tie this activity group to the testing. So while we're trying to expand Ontario, the testing to a larger population, maybe is there any way that you can incorporate this by saying that those who are more active should receive the testing more regularly?
So in that second video I showed, the green curve stayed up fairly high and the red curve went down fairly low. And so that was the idea, that the red curve was going very low as tau1 got small, and was saying that the social distancers, their risk of getting infected was actually getting quite small. It was a very small fraction of the population getting infected, whereas the green one stayed higher. And that suggests that the people who are out there being more active, they're quite clearly at a higher risk of getting infected, and it makes sense for them to get tested.
But they're also passing the infection to the other populations, the other group, because of their infection.
Yes, absolutely. If we built a wall between the distancers and the non-distancers, then for some of the parameter values I had, the non-distancers, the disease would just die out of that subpopulation on their own. It's only because of the interactions they're having with the, I think I said that backwards. The social distancing group on their own would not sustain the epidemic. It's only through their contact with the non-distancing group that they were continuing to get infections. And the non-distancing group was pretty much sustaining the epidemic on their own. So, a really good question is, where do you target the testing? The news in the last couple of days, Premier Ford is asking people in any hotspots to, won't tell us where the hotspots are, but if you're in a hotspot, to go and get tested if you think you need a testing. And I think that general access to testing will be important. Among other things, it will help us figure out what is the population level incidence of the disease in the population. We're kind of stumbling in the dark in that aspect, because all we have are really the self-identified cases where people are going into hospitals because they feel sick, and we need to know how many asymptomatic or mild cases are there.
Great. Any other questions, comments?
I have a.
So thank you very much. Yeah, go ahead. Yes, this is Adam Messer.
Yeah, thank you. Sorry, I have a quick one. I really enjoyed your talk, Connell.
Thank you.
And I have sort of a high-level question, I guess. It seems to me like if you're going to kind of design effective policy, it's really important to know the C parameters and the F parameters. I think that was one of the big take-homes. And it also strikes me that, like, without using one of these contact tracing apps that Apple or Google have, it's almost impossible to get those numbers. It also seems like we need those numbers to really get on top of these kinds of outbreaks. Do you have any kind of thoughts on that? Like, do we need to go down that road to be able to get the data that we need to really manage these outbreaks in the future? I know this is kind of, and like, this is not exactly what you were talking about, but I wonder if you have any thoughts on that.
So if they bring in those apps, there would be a route where that could be used to get data for the type of thing that I'm discussing here. And that would be helpful. And that would be helpful for figuring out what policy should be. I think a much more useful aspect of those apps is their direct use of contact tracing. And that's one of the things that seems to be fundamentally important for battling the disease as we start to open things up. The population, we think, is nowhere near herd immunity. So if we just open things up, there's nothing about the situation now that makes it any better than it was 2 months ago, except that now there's a lot more infected people out there. So in fact, it's a lot worse. The one thing that's been going well so far is that there has been a lot of distancing to keep these contact levels down. But if we open things, there will be a lot more infections, I believe, and the contact tracing will be very important for that. It would feed in here. So is there that way or some other way to get good data on these? And how important is it to get good data for the heterogeneity I'm discussing? I think it would help, but I think given how hard it would be to get that data, just a certain level of awareness of the phenomenon could be sufficient to know that certain predictions have to be either moved up or moved down based on how they're being calculated. Yeah.
Thank you.
So, Connell, so Professor Amy Grail from Guelph, University of Guelph, I think she is conducting a very intensive survey in terms of getting the information about the contacts during the social distances. So maybe we'll see if I can one day get her talk to the seminar, but she will be the real expert talking about the contact patterns. Any other questions, or I think Kuma, any other comments before?
No, I think it's very good. That's just maybe express our appreciation to the speaker, and if there's a preprint that you could post, we'd probably be interested in having a chance to look at it.
Okay.
Thank you very much. Then we'll see you next week. We're going to have another speaker from the Utrecht, Netherlands, the Center for Infectious Dynamics. She's going to speak next week as well. Thank you, and see you next week.
Great. Thank you, everyone.
Thank you. Bye.